What you will hear from us today is an introduction to modeling of wastewater treatment plants using WEST. The webinar is hosted by myself. My name is Fabio Polesel, and by my colleague Enrico Remigi. The webinar will consist of a presentation which will last approximately 45 minutes, more or less, and the Q&A session, 15 minutes more or less at the end of the after the webinar. As you can see, as all of you participants can see, you have a bar in your Zoom features where you can chat with us. However, I would not recommend to do so unless there are some specific issues. A Q&A button where you can post questions that will pop up in your mind throughout the presentation. We'll try to address them during the presentation or at the end of the presentation. And that's basically it. So a little bit of introduction about ourselves. We are based at DHI, and we both work with process modeling and wastewater related challenges. So DHI is an institution, is a 55-year-old organization, so quite old, working with water in many different aspects. So as you can see from this slide, it covers quite a wide span of water-related issues worldwide. Specifically, Enrico and I work in the urban water section, and we deal primarily, but not only, with wastewater. So we deal with wastewater from an integrated perspective, starting from treatment, from collection systems, throughout treatment to discharge and impacts on environmental recipients. Today, you will hear from us mostly, but not necessarily only, on wastewater treatment plants and how we can model them and what are the advantages and the tools that we can use from modeling exercises. So the agenda of the webinar covers a number of points. First, we will start with an introduction to wastewater treatment plant modeling and a little bit of history. Then we will go deep into WEST, DHI software for wastewater treatment plant modeling and simulation. We will look live at the interface and how we can implement and run wastewater treatment plant model simulation. Then Enrico will provide you some information on some advanced tools and experiments that are part of the WEST product suite. Enrico will also provide you with some hints or some basic information of applications of WEST for modeling and what was the benefits in the real world brought by such approach. And we will conclude with some final remarks and, as I said before, with some questions and answers to participants. Okay, so let's start with the first point of our agenda. Wastewater treatment plants. Wastewater treatment plants are closed systems, so they're quite not very difficult to monitor. And processes occurring in wastewater treatment plants are quite well known. So why do we need to model wastewater treatment systems? Well, there's different reasons. First of all, to understand the system better. As I said, they are closed systems with well-known processes, but they can be relatively complex, especially full-scale treatment systems. So a model can provide us with a better understanding of the behavior of the system. We can use models to evaluate and predict the behavior of the system in different scenarios under changing boundary conditions. For instance, how does the treatment plant perform if we have increased loading in the influent. And eventually, models can be used as decision support tools to support upgrade and retrofitting of treatment systems, optimization and implementation of control strategies. So in practice, models can be useful at different stages of a life cycle of a treatment plant. So they can be useful in the design and in the retrofitting stage. For instance, we can use models to evaluate different treatment plant configurations, verify design that is normally carried out at steady state, assess the treatment plant capacity and verify whether it's sufficient under different scenarios, and evaluate alternative solutions for retrofitting. They can also be useful in the operation phase. So when a treatment plant is already operational, we can use models for different purposes. To minimize the use of resources, to estimate important emissions such as greenhouse gases, to maximize energy and resource recovery, to test and implement control strategies, and also to understand whether online monitoring systems like sensors behave as we expect. So in a few words, we can use models in the operational stage of a treatment system to optimize, to control, and to troubleshoot. Let's take a step back and let's look at the history of wastewater treatment collection and treatment systems. So there's been consistent development in technologies, in process discovery, especially in the last 100 years, in the last century, since activated sludge process was discovered, since trickling filters came into operation, right? So if you focus on the last century, when did models become of relevance? Well, we can circle this date, that's in the mid-80s. That's a key date for process modeling, for modeling of wastewater processes and treatment. It must be said that research on modeling of wastewater processes, especially biological processes, already started in the 40s with, for instance, the identification of the Monod equation, and in the 70s through research conducted in the US or in Sweden at Lund University, for instance. But mid-80s is a key date for process modeling. So why is it a key date? In 1985, an important seminar took place in Cole Cole, so not so far from where I'm sitting right now, just a few kilometers, as you can see from the map. And the outcome of the seminar paved the way for the definition of the first activated sludge model number 1. So all the research efforts from the previous decade culminated in the definition of a standardized model. So a model with a standardized description of biochemical processes happening in activated sludge. And what was the forecast use and benefit of a standardized activated sludge model? On the one hand, to help operators understand the behavior of treatment systems and predict it. And on the other hand, to guide research, to help research discovering new things in the field. Okay, so what is a key concept, a key element of standardization of activated sludge model? It's the concept of fractionation. So lumped pollutants or major pollutants like COD, nitrogen, and phosphorus, as we normally think treatment composition with, are fractionated into different subfractions. based on whether it's small or large size molecules, whether they are it's degradable or inert fractions, whether it's inorganic or organic substrates, for instance, for nitrogen and phosphorus. Okay, so the major fractions, COD, nitrogen, and phosphorus, are fractionated into subfractions. And these subfractions constitute the state variables used in activated sludge models. Activated sludge models are normally summarized, contain a lot of information, such as processes, state variables, and so on, which is summarized in the matrix, in a matrix, like the one that you see here. So this is a process matrix, a Guyer matrix, or a Peterson matrix. And such matrix summarizes all the information related to activated sludge models. So we have state variables, which are the concentrations of different fractions. We have processes, biochemical, microbial growth, microbial decay processes, hydrolysis. We have process rates, and we have stoichiometric coefficients that help us understand whether continuity is verified within the model. So there's conservation of mass. Okay. So if we compare the history of wastewater treatment with the history of process models, we see some similarities. So first, the initial focus was on organic carbon and nitrogen, which was touched by activated sludge model number 1. Subsequent focus on refocusing on other components like phosphorus resulted in the definition of new activated sludge models, number 2 and number 3, dealing with biological phosphorus removal. And subsequent focus on sludge treatment and resource recovery resulted in the definition of anaerobic digestion model number 1, or ADM1. Okay, so activated sludge models describe, however, only a part of the processes that happen in a wastewater treatment plant. And they need to be combined with models describing solid liquid separation in settling tanks, sludge treatment, biological sludge treatment, and it needs to be considered also that the influent with a certain quality and quantity is treated in the wastewater treatment plant, And normally this quality and quantity varies over time. So influent entering a wastewater treatment system is dynamic, right? So a lot of information needs to be considered for modeling a wastewater treatment plant properly. And this brought to the definition of computing tools, like modeling software tools. So WEST is one of these wastewater modeling tools. WEST stands for Worldwide Engine for Simulation and Training, and is a dynamic simulation tool of wastewater treatment plants. It was conceived in Belgium at Ghent University in early 90s, mostly, but not solely, for research purposes and training of wastewater treatment plant operators. But through the years and through the decades, it has developed to incorporate real-world experience and the needs of practitioners, of operators. So it's been increasingly applied to provide solutions to the challenges of treatment plant, of treatment utilities and industry. So WEST itself includes different products or different tools. We have a main application where a model of a treatment plant can be built and simulated. So a layout can be edited and an experiment can be executed. So a model can be built and simulated. And this is what we call a modeling project. Then we have also block editors and model editors that will be presented by Enrico later. So now let's focus on the main application, which is itself called WEST. Before jumping into a live show of the interface, let's see what is behind it. So we have a standard model library, which includes many different unit processes or blocks that summarize different technologies, biological, physical, chemical, used in a wastewater treatment system, and additional components of high relevance, such as sensors and controllers. And behind it, we also have different process models, depending on the objective of the modeling study. So we have models of different complexity, starting from activated sludge model number 1, up to the integrated urban water systems model library. So allowing to model an integrated systems with sewers, a treatment plant, and a river, a recipient. So let's quickly move to the WEST interface and see how it looks like. So this is how the WEST interface looks like, the guided user interface. So what you see here is a layout editor, which includes on the left a block library. So a summary of all the blocks that are available to build a wastewater treatment plant layout. We have blocks summarized in different categories. So for instance, for biological treatment, we have activated sludge and biofilm systems and membranes. For instance, separation, we have primary and secondary clarifier, and again, membrane separation. We have flow splitters that allow to describe splitting and combination of flows in pipes in a real treatment plant. So how are these included in the actual layout? It's simply by drag and drop to the interactive layout editor. Yes, so what you see here is a already presented in this project is a pre-denitrifying activated sludge system, so quite a conventional activated sludge system, and it comprises different blocks. So we have an influent block where we can upload an influent file describing wastewater flows and concentrations of different components. So that describing what enters and is treated in the treatment plant. We have a pre-denitrifying and a nitrifying reactor. We have an internal recirculation for recirculation of nitrate, a secondary settling tank, sludge wastage splitter, and an effluent and waste sludge block. Okay, you also see some strange or funny blocks in some parts. So there's 3 blocks, 1, 2, and 3 denote the sensors that are used, some virtual sensors that can be placed at different locations of the treatment plant, so they retrieve information of the stream that goes through them. Okay, so let's try to simulate this treatment plant. What you can see here is a steady state and a dynamic simulation. Before I forget, it should be mentioned that we have different layers. So if you look here at the bottom right, we have different layers, a water line and a sludge line and a control layer. So you can see that the control layer is currently made not visible. So if I activate this layer, you can see that some additional blocks pop up. So these additional blocks are an aeration controller, so a controller that we can use to set a defined dissolved oxygen concentration in the aeration tank, which is, for instance, set to 2 milligrams per liter. And we have an operational cost block. So you can see that it's connected with different blocks in the layout. So it retrieves information from the different blocks to estimate the consumption of energy and the operational cost of the wastewater treatment plant. So to go back to the simulation, to the model simulation, we can run different types of simulations. A steady state simulation, which assumes that we have an influent with constant flow and constant concentrations and loads of pollutants. So that's normally an auxiliary simulation that we can run. And that's normally quite fast. You can see we are simulating 200 days in a few seconds. So it shows how powerful the engine is. And then we can run a dynamic simulation, which now considers dynamics in influent quantity and quality. And what you see here is a dashboard which summarizes the different types of graphical output that can be generated based on the model simulation results. As you can see, the output is updated in real time. And we have different types of plots, line plots, for instance, where we plot the removal efficiency of COD, nitrogen, and TSS, concentrations in the effluent of different fractions, like readily biodegradable COD, ammonium, and nitrate, and of lumped components, so effluent concentrations of COD, nitrogen, and TSS. We also have a bar graph that provides differences in TSS concentrations at different depth in the secondary settler, and we have a table. So you can see we can generate many different types of plots and output tables. These additional graphs summarize the information on energy and cost estimations. So what you see here on the left is the contribution of different sources of energy consumption on the total energy consumption from the treatment system. In blue, you see aeration, which normally provides for 60–65% of the total energy consumption. In orange, it's pumping related energy consumption, and in green is reactor mixing. On the right, you see the cost. It's an increasing graph with the 1-day frequency, and that's because we decided to simulate the daily operational cost. So in blue, you should take the value at the end of 1 day that would tell you the cost related to aeration, pumping, and mixing within that day. So it's a cumulative function. So in this specific case, we can see that there's an estimation of around 500 euros, 400 to 500 euros or dollars, depending on the currency for aeration. Okay, so this is about energy and cost estimation. So some more insights on the operational performance and efficiency of operation of the treatment plant. Let's run another simulation here. So these graphs that you see here denote the ammonium on the left and the nitrate on the right, concentrations in the effluent. And what I would like to draw your attention on is that we can store graphs from previous runs. So for instance, if we change the temperature in the anoxic or in the aerated tank, which is now 20 degrees, and we set it to 7, for instance. Let's see if I manage. You will see that the previous graph has been stored, and we have a new run, a new graph generated for the new run. So the new graph that you see being generated in real time is the graph denoting the model output at lower temperature. So not unexpectedly, we see an increase in the ammonium concentration in the effluent when we operate at lower temperatures, quite low temperatures. So if we set back to 20 degrees, you will see that the graph at 7 degrees is stored, and the new plot is generated for 20 degrees. Yes. I will also finally would like to draw the attention to some features that are embedded in WEST to facilitate users in reporting and parameter setting and so on. So what you see here on the top bar, it's 3 embedded functions: notes, reports, and workbook. So if we open notes, you will see that a number of spreadsheets are open up where we can write notes about the project that we are working on. So for instance, I wrote this note on live from webinar, and the note will be present, so we can always access this note to keep track of different versions of the project, for instance. We can also generate a report based on the information that is provided. So in the report, we can decide to include different types of information related to the project. This could be, for instance, the notes that we wrote, a picture of an image of the layout that was implemented, and different plots. Okay, so you can see that the report is generated with different elements that I've ticked on, and this report can be saved as a regular document. So you can see that the report includes our notes, some general information, the note that we wrote, the layout, and the different blocks, and the different plots that we decided to export. Last but not the least, I would like to introduce you to the workbook function. So the workbook function is a feature which includes a workbook or a spreadsheet embedded in the WEST project. So for instance, and this spreadsheet can communicate with the project, with the layout mod, with the modeled layout. So for instance, we decide to set the internal recirculation flow to 77,000 cubic meters per day, and we want to export to the workbook the output in terms of effluent nitrate obtained at the last data point, so at the end of the simulation. So if you see that if I change the internal recirculation flow rate to 50,000 cubic meters per day and I refresh, you will see that this parameter value is updated also here on the right. And on the right, you have all the information related to the flow splitter for the internal recirculation. And if I run the simulation again, you will see that the output will change. So you will see higher, not unexpectedly, a higher effluent nitrate concentration in this cell. Okay, so it increased by approximately 1.5 to 2 milligrams per liter. Okay, so that's it. There's much more to explore, many more functions to look into, but I'll now like to leave the floor to Enrico, who will proceed with the second part of the presentation.
Right, so what I am going to show you is this, what experiment types are included in WEST. What Fabio has shown you so far is the base experiment. It's called objective evaluation. You have seen the steady state and the dynamic simulation. There's a little bit more to the objective evaluation, and there is the possibility of defining in a completely free manner an objective, a cost function, that is computed with every simulation. So you can define a complex objective that could include indices in relation to the effluent quality, the energy consumption, the sludge production, resource recovery, whatever, all combined and weighted in a appropriate way. And then you can characterize one simulation with one number, with one objective, and on this ground you can compare different scenarios, different setups. This is the base experiment. And then there are 5 virtual or advanced experiments, as they are termed in West. Sensitivity analysis of 2 types, local and global, parameter estimation, scenario analysis, and uncertainty analysis. The underlying principle is the same for all 5. So they will evaluate the impact of changing a set of parameters on a set of variables. So the idea is that you select 1 or more parameters, you instruct West how to change these parameters for every run, and then West will run multiple simulations in sequence and evaluate a set of variables that you also need to select, and therefore quantify the impact of the changes on the parameters. Sensitivity analysis is essentially used to identify the most sensitive variables of the model to a set of parameters. Sensitive variables will be the variables that you should go and measure on the real plant in order to calibrate those parameters, because those variables contain the largest amount of information connected to those parameters. So it's worth measuring those variables as opposed to other variables that have no relation or hardly any relation to the parameters. Parameter estimation you can use, as I said, to calibrate the model. So a combination of these 2 experiments is effectively a means to automatically calibrate a model. You can also use parameter estimation to optimize the typical process optimization exercise, to optimize a layout, a process. A scenario analysis to compare scenarios, and uncertainty analysis will rather show you a typical output that makes it maybe more clear. Examples of outputs of the different experiments. This is a typical tornado plot of a global sensitivity analysis. On the left-hand side here, you see nitrate in the effluent, concentration of nitrate in the effluent. I highlighted 3 parameters that have a big impact on this variable. Oxygen concentration in the aerated tank with a positive sign. So increasing aeration will increase nitrate in the effluent, which is I mean, everyone knows based on experience. Increasing the mixed liquor recycle will decrease, will be effective in reducing nitrate concentration and so on. So this is a type of output that you can expect from sensitivity analysis. Parameter estimation, or model calibration in this case. This is an example that uses 2 kinetic parameters with a certain guessed starting value of 1, whatever. The error, so the distance, the difference between the set of measurements that you see here with the symbols in this plot and the corresponding simulated variable will be big in the beginning, and as the simulation, the experiment actually proceeds run after run, the objective, so the error in this case, will decrease. The value, this estimated value for these two parameters will progressively reach its asymptotic value, which will then be the calibrated value that you will input back into the model. Scenario analysis is pretty straightforward. In this case, a 3D plot where you look at the impact of two parameters here. Oxygen concentration again in the aerated tank and size of the anoxic tank versus the concentration of, again in this case, nitrate in the effluent. So you see that by increasing the aeration set point, you will of course increase nitrate, but then if you have a larger anoxic volume, you will also achieve a decrease in nitrate concentration in the effluent. Uncertainty analysis offers this type of output, where you have concentration in on the horizontal axis here and percentage of time in violation on the y-axis. The first qualitative information that you can derive from this plot is the width, the amplitude of this, the area between these curves, and this denotes the confidence region for that variable. So this tells us, in this case, it's quite relatively big. So the model is not particularly sensitive to this. Well, it's very sensitive to this variable, so it's not very accurate for this variable. And another type of information that you can derive is that if you move along this line, this is a 95th percentile. Sorry, my mouse keeps moving. If you sit on this 95th percentile line, you can say that this concentration will not be exceeded for more than 20% in this case of the time with 95% certainty. This is the type of output that you can derive from an uncertainty analysis. And this is an overview of where each of these advanced experiments would fit in a modeling exercise, whether it's calibration or application of a calibrated model. What Fabio has demonstrated so far is the main application of the WEST product suite. So WEST itself is the modeling environment where you set up the layout and execute the simulations and the experiments. There are additional tools, and the main ones are this block editor and the model editor. The block editor gives access to the icon library, so you can very freely, again, everything is very open in WEST, define new icons or import new or images that you might have, and just associate a couple of some pieces of information like the terminal type, data type, and then WEST will automatically incorporate the new icons into the library, and they will then become available to set up process layouts. The other tool is called Model Editor, and this gives access to the model library. At the very least, to look at a model, how a model is implemented, what are the equations. Everything in WEST, all the models are completely visible. There's nothing like a black box in WEST. One way to look at the models is through this GUI matrix editor. This is exactly the counterpart of what you have seen a few slides before, where you see the processes on the rows, the state variables, the components on the column, and the body of the matrix represents the stoichiometry, the rate equations in the last column. Essentially, to modify a model, you can simply write the equations as you would on a piece of paper. You don't even need to understand or know anything about the modeling language, the specific modeling language that is used for the model library of WEST. Of course, there's also a more traditional code editor that one can use. with all kinds of editing support that you would expect from a code editor. A couple of additional tools are also available, but they are, I would say, less important than this, the previous tool. We have collected here 3 examples of relevant case studies. We showed you before different areas of applications of waste over the lifetime of a treatment plant. And we have then isolated these 3 examples. I will show you a few things about each. First is this OSCAR dashboard. OSCAR is a control algorithm and effectively an instrument that allows you to optimize aeration in intermittent nitrification, denitrification activated sludge systems, developed by one of our clients in Italy. What they did with waste is to implement the logic, the algorithm of the instrument and test different conditions, and they routinely use this model to optimize the specific settings on a given plant. And by doing this, you see here example of outcomes in terms of treatment efficiency, energy consumption, and sludge production. Another type of application is this study on 4 small, relatively small treatment plants in Denmark. Here, the challenge was to decide whether it was more financially viable to invest in more traditional engineering, so construction and expansions, upgrade of the treatment works, or invest in sensors and automation. And by studying these systems, by modeling these systems and simulating different conditions, we proved that the second option was definitely the best, with a overall return of investment that is very low, I would say, around 1 year. And specifically, these 3 cost items were evaluated: cost of resources, energy and chemicals, cost of effluent taxes. In Denmark, you pay for every kilogram of pollutant discharged into the environment, and the overall depreciation of the treatment plant. And you see here that plus minus the return of investment on this type of investigation was around 1 year. A third case study is this one. Again, also in this case, part of the goal was to implement in waste, in the waste library, a specific control algorithm to optimize aeration, but this is one part of the challenge. What I'm going to show you here is a custom user interface that was built on top of a waste model. If you remember what you have seen earlier in waste, waste is a typical engineering modeling software that is perfectly, I would say, I hope everyone agrees, very user-friendly, but for a relatively knowledgeable modeler or engineer or user. If you should ever need to deploy a model to a less experienced or less knowledgeable user, like an operator for training typically, you would probably prefer a more user-friendly interface, and this is an example that can be built in waste. In this case, we had an aerial view of the plant with clickable areas. Depending on which one was clicked, the corresponding output, graphical output, was displayed. And here there's a small dashboard that only enables the few control handles that the operator in reality has access to, and all the rest, all the complexity of the model is hidden. Now I think we have 1 minute. So what are the benefits in conclusion of WEST? Well, for this type of user, looks like yeah, like an advanced user or more a nerd maybe. WEST is an extremely powerful simulator. The engine, the engine of WEST is very powerful. You can see on average conditions, you can simulate 1 day in about 1 second. It's a completely open tool, both the model library and the user interface. You can interface WEST with virtually any other third-party component, SCADA system, Excel, internet browsers. For a more professional, less academic maybe type of use, WEST is very useful for the typical applications in this domain: design on the one hand and operation. This for design verification, capacity assessment, scenario analysis, or process optimization, both looking at energy and cost, and to evaluate different control options. Two small other things I wanted to mention. We provide support, technical support, 24/7. So anytime you should ever have a question, you will get an answer very quickly. And we also provide a variety of trainings from online type of training to on-site of different types. Thank you.